Okay, this is video 2 for week 2, Math 0110. Continue in the next subtopic on something called piecewise functions. Piecewise functions are a type of function that can't be described as just a single f of x equals something. I'll show you some pictures of piecewise functions before looking at them defined algebraically. They're generally ugly like this. So they'll do something like quadratic type behavior in one spot, linear behavior in another spot, maybe quadratic and hyperbolic behaviors in other locations. They might have holes, and they have jumps, and they have places where they're discontinuous, places where the y value changes abruptly as we cross a particular x coordinate, places with what are called vertical asymptotes, where the y value of the function goes to plus or minus infinity. And here's another one. This one is explicitly stating what the pieces are. There's a quadratic piece, there's a linear piece, and then there's a single point floating off in space all by itself. So they're not necessarily nice looking functions, but functions that are important. So here's an example of a piecewise function, not really a realistic example, but just to give you an idea what the function looks like algebraically. We have a retail chain experiencing slow growth for a few years, but then its competitor goes bankrupt and it starts doing better. So this graph might have described the situation of Canadian Tire a few years ago when Target left Canada and its sales prospects improved because they were no longer competing with someone in the same market segment. Anyway, this is far too simplified a model to explain that, but it captures the main idea of a function that is describing something in reality that behaved differently at some time than in some other time. The question asks us to plot the function, and that's it, just make a plot. Okay, so to make a plot, I'm going to do two things. I'm going to make an x-axis, a y-axis. Well, first I made the y-axis, that's okay. So my x-axis, my y-axis, I have to make sure I can put all the required x values in. 1, 2, 3, 4, 5. I'll label them. So notice my piecewise function starts at x values of 0 and ends at x values of 5. So I have to make sure that my graph has that. Actually 6, it goes higher, right? I'll do a little bit more than that. Actually, let's go make it larger. You know what? Let's make a bigger graph than we have to. So 1, 2, 3, 4, 5, 6, 7, 8. Say hello. How high do we want to go? 8, 9, 10. And I'll hold off on labeling the y-axis until we figure out how many x values we're actually going to plug in here. Okay, now I'm going to make a table of values. I'm going to plug the x values in and get the y values out. So here's my x value, my corresponding y value. So my x value, it says that the function is equal to x plus 7 for all x values between 0 and 2. So I'm going to put a 0, a 1, and a 2. Those are the integer x values between 0 and 2. There's others, but let's just leave that alone. Let's just use integers to make our lives easier. And then for the next piece, it says that the function is given by x squared plus 5 for x values between 2 and 5. And actually that means we only go up to 5. The function doesn't exist outside that range, outside that domain. Okay, then I'll put 3, 4, 5. Now we're going to plug the x values in. So I plugged 0 in. 0, we have to decide which piece of the piecewise function to use. The part on the right-hand side with the inequalities, that's telling us, based on the x values, telling us which piece of the function we should be plugging that x value into. It's like a sorting bin. is this x value going here or is it going here? Am I doing this to it or am I doing that to it? So since 0 is between 0 and 2, we're going to plug it into the first part of the piecewise function, x plus 7. So we get 0 plus 7, which is 7. So I'll just keep going before I start graphing these. Now x equals 1. I have to do a check. Is 1 between 0 and 2, or is 1 between 2 and 5? Well, 1 is between 0 and 2, so it's also going to go into the first part of the function. So 1 plus 7, which is 8. Okay. Now we'll do it one more time. 2. 2 is between 0 and 2. Notice that the equality is on the top piece of the piecewise function and not on the bottom piece of the piecewise function. So I'm going to use the top part. I get 2 plus 7, which is 9. Okay, we might as well graph those first three. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16. Maybe that's enough. Maybe it's not. I don't think it's enough. We'll see. Okay, so 0, comma 7. 2, 1, 2, 3, 4, 5, 6, 7. So there's the first one in year 0. Then in year 2, it's up here. For year 1, it's at 8. In year 2, it's at 9. Okay. 2 and 9. Okay, now we'll get the rest of the values. We'll plug 3 in. So 3 squared is 9. 9 plus 5, 14. And then, I skipped the important part. Where do we put 3? Do we put it in the top or do we put it into the bottom? Well, 3, it's not between 0 and 2. 3 is between 2 and 5, so it fits the second inequality. So 3 squared plus 5. 9 plus 5, 14. So 3, 14. And then 4, I'm going to plug 4 in. 4 squared plus 16. I'm plugging 4 into the second piece because it fits into that second inequality. What am I doing? 4 squared plus 5. 4 squared plus 16. So 16 plus 5, 21. And my graph is already inadequate. So I'm going to put that up here. It's around here somewhere. And then 5, I'm going to plug 5 in. 5 squared plus 5, so 25 plus 5, 30. And that's going to be way up here. I can't even graph that. Put it there somewhere. Okay, and then I can connect the curve. The first part is linear. Second part is a quadratic. And I'm going to do something that is going to bother you a little bit. I'm going to plug in 2 into the bottom piece. And I shouldn't plug 2 into the bottom piece. So let's think about plugging in 2.1. So that'll be 2.1 squared plus 5. So that's a little bit larger than 4 point something. So I'll say is approximately equal to 9. So if I plug in something a little bit larger than 2, I'm going to get something very close to 9. So 2, 9, it's the same point. So I'm going to continue the curve from that point. So it starts as linear and moves to quadratic. My graph is terrible. I didn't use a ruler. I didn't use graph paper. I made no effort to make it pretty, and that's okay. The main point of this example is to show you how a piecewise function works. And it works by first choosing the x value, then deciding based on an x value where, adjust my camera a little bit, which piece do you plug that x value in for. Okay, next, function is another piecewise function. F of x is 10, so a y value of 10 for only x equals 1, and it's a y value of x squared plus 1 for x not equal to 1. What does this look like? Well, the bottom part, x squared plus 1, is a parabola. It's shifted up 1 unit. The problem with the parabola is it has a hole cut into it. You can see that in the graph, and the hole is at an x coordinate of 1, because it said the piecewise function says it's equal to that graph except at 1. At exactly that point, the y value is exactly 10. So that's how you would graph this piecewise function. If the question asked, what is f of 1? The answer would be 10. What if it asked, what is f of 1.1 or f of 0.9? Well, the answer would be the number that you get by plugging 1.1 or 0.9 into the bottom part of the piecewise function, since 1.1 is not 1 and 0.9 is not 1. But at exactly 1, the y value is exactly 10. All right, another aspect for functions is the distinction between things that are functions and things that are relations. We are going to talk about relations inside the course as distinct from functions. It'll be a bit later. What makes a function instead of a relation is that a function passes something called the vertical line test. What the vertical line test is if you take the graph and you take a vertical line and you scan the vertical line going left to right or right to left, you go back and forth with that vertical line. So a vertical line is a line going up and down, but you scan it left and right. What will happen as you scan left and right is that vertical line will cross the graph at most once. It may not cross it at all. It may cross it exactly once. And in either case, it doesn't violate the vertical line test. But as soon as that vertical line at any location crosses the function twice or 3 times or 4 times, then it's not a function actually, it's a relation instead. So on the left-hand graph is a relation. The vertical line in red has crossed it 2 times. And it only has to happen in one location for that to violate the vertical line test. So on this slide are 4 pictures, and the task is to determine which ones are functions, which ones are not functions. Top left, you can imagine taking a vertical line and scanning it back and forth across the page, and it's only going to cross once, so it's definitely a function. Same with the bottom right. You can scan a vertical line back and forth, and so you only get one y value at every one of those vertical line x values. So a vertical line is a line of constant x. So it's like you're plugging an x value in, you're asking what is the y value. If it crosses once, that's the y value at that x value. If it crosses twice, well, there's 2 y values there. What happens in the bottom left? Well, it's going to cross twice, so it doesn't qualify as a function. The interesting one is the top right. Recall that if we put a hole in the picture, it means the function does not exist at that point. If we fill in the y value with a point floating in the middle of space, that means the function's y value is equal to the y value of that point at that x coordinate. So when we perform the vertical line test on the top right graph, you know, the first problem area that you might be concerned about would be at x is equal to 1, you put that vertical line here, and it actually does not hit the function at that open circle. It passes right through it, but it does head over here. So okay, it passed that vertical line test, crosses once. Okay, and I will try the next one. I'm going to pass through this point. Oh, doesn't touch it, goes right through it, and then it touches this one. So it crossed exactly once. And the last point is at x is equal to 4. So we try to pass a vertical line there, and it doesn't touch it at all. But remember, the vertical line test, the only thing that makes the graph fail the vertical line test is if it crosses more than once. It's not crossing at all. So I'll just circle, crosses once, and does not cross at all. So the answer is that this is a function. The vertical line test doesn't trigger a negative response at any of the x values. That last graph is an example of a discontinuous function, like some of the pictures that were in the earlier part of the lesson. The language that's required to talk about discontinuous functions isn't something that we've developed yet. What we need is an idea called a limit. It's one of the next things we'll do. So we'll come back to this. What else do we do with functions other than graph them and plug them in, or graph them, evaluate them, and determine their domain? What other things can we do? Well, we can take, let's say, two functions and combine them in different ways to create new functions. For example, we can add two functions together to create a new function. It's called a sum of functions. We could subtract functions as a difference of functions to create a new function. We can multiply them to create a new function, or we can divide them to create a function. The shorthand notation, which I'm not going to use inside this course for combinations of functions, those are shown on the right hand side. So f of x plus g of x sometimes is written f plus g of x. F of x times g of x is sometimes written f times g of x. I really don't like that notation, but I'm explaining it here because it's in the book. Now, when you add two functions together, or subtract two functions, or multiply two functions, the domain of the resulting function is going to be the most restricted of the domains of the ingredient functions that you use for the combination. So it'll be the smallest of the, it'll be take all the restrictions that are for f of x and all the restrictions for g of x and apply those restrictions to the new function. The quotient of functions, or the division of functions, introduces a new type of domain issue that is not originally in f of x or originally in g of x. And that domain issue is an additional potential to divide by 0. So nothing there. Don't worry about that. You'll be asked, if asked for a domain, you'll be asked for a domain of a function. You won't be given two functions and ask for the domain of the combination of those two functions. Just again, something that's in the book, and I wanted to explain it a little bit more than what's in there. Okay, so let's go through that process for these two particular functions. Let's combine f of x is 3x and g of x is 12x squared plus 9x cubed plus 6x. Okay, so f plus g, that's 3x plus 12x squared plus 9x cubed plus 6x. We're not done yet. We can combine like terms. The 3x and the 6x are like terms. We can merge them. We're going to get 12x squared plus, well, I'll put them in the correct order. The highest power of x should go first, so 9x to the power of 3 plus 12x to the power of 2 plus 9x. And I'm going to highlight that these two turned into this one, because I did two steps in there. I changed the order of addition and I combined like terms. Okay, next one is subtraction. Change my color. So that's going to be 3x minus. Now we're subtracting the entirety of g of x, all of it. So I'm going to put brackets to make sure that every single piece gets subtracted. 12x squared plus 9x cubed plus 6x. So that's going to be 3x minus 12x squared minus 9x cubed minus 6x. So I did an intermediate step just to display the subtraction. And now I'm going to reorder the terms. I'll put the negative 9x cubed in front, the negative 12x squared next, and then we'll combine, using the trusty green highlighter, the 3x and the minus 6x. We'll combine those into whatever is going to go here, which is minus 3x. Okay, next one, f times g. So that dot means multiplication. So that's 3x multiplied by, well, I better put the whole thing in brackets again, so I multiply every single piece. 12x squared plus 9x cubed plus 6x. And we're going to expand that in, that it's multiplying by every single piece that's in there. 3 times 12, 36. X times x squared, it's x to the 1 times x to the 2, which is x to the 1 plus 2, so x to the power of 3, plus 3 times 9, 27, x to the power of 4. Again, add the exponents. 3 times 6, 18. X to the 1 times x to the 1 is x to the 1 plus 1, x to the power of 2. And I'm going to do one more step. I'm going to put them in the right order. So 27 x to the power of 4 plus 36 x to the power of 3 plus 18x squared. Just to put them in the order that the back of the book would have if you're doing your homework. Okay, next one, f divided by g. I'll switch back to purple. So that's going to be 3x divided by 12x squared plus 9x cubed plus 6x. That's the answer, but we can do some other stuff. It can be simplified, but I won't. I was tempted, but I don't feel like it. I'll just write can be simplified. What you would do is you would common factor the denominator, and then cancel. Okay, and then the last problem here. Check the time. Ooh, okay. I want to keep these to 20 minutes, but it's not happening. G over f. So we're reversing the order of the division. That'll be 12x squared plus 9x cubed plus 6x, all divided by 3x. That's the answer. We can simplify it, and maybe I'll do this one. Maybe I'll simplify it. So I'm going to do the common factoring step. How much can we take out of the top? Well, 12, 9, 6. The common factor that I can divide each of those by without creating a fraction is 3. And the highest power of x that appears in all three expressions is x to the power of 1. Now what am I left with? I'm left with a 4, since 12 divided by what I factored out. 12 divided by 3 gives me 4. What's the power of x? It was x to the power of 2. I took one of them out, so now there's one left. Plus 9 divided by 3 is 3. X cubed divided by x is x squared. And then 6x divided by 3x is 2. Now we still have that division by 3x. Now I'm going to do a cancellation. And the trick is that this does equal 3x squared plus 4x plus 2, but 4x not equal to 0. Because if x is equal to 0, that step will be canceled, the 3x on top and the 3x on the bottom. That cancellation is a division. And if x is 0, then we would be dividing by 0. So for these two things to be equal, before and after the cancellation, before the cancellation, 0 is not in the domain. After the cancellation, 0 is still not in the domain if we want these two functions to be the same. So part of the function is that statement that x cannot equal 0. We'll stop here and continue in the next video.